In this lecture, we're going to cover Units 11 and 12. Unit 11 is going to cover the apothecary measurement and conversion processes. So we've already done conversions. We've been working with those. So after this lesson, you should be able to convert among apothecary, household, and metric measurement systems, as well as use the correct number formats for the measurement systems and properly format your answers. All right, so let's dig into this. Remember, I talked a little bit about the apothecary system a few units back when we introduced conversions. And the apothecary system was the medication measuring system used in England in the 1700s. At one time, household units were used as a means of converting from the apothecary system. So it's currently being replaced by the metric measuring systems to avoid miscalculation of dosage and consistency for drug labeling for healthcare practitioners. In fact, some training programs no longer include the apothecary measurement because of the conversion to metric units and the use of household measures, which are simpler and less likely for errors. Also, the Joint Commission has placed the apothecary symbols on the Do Not Use list. However, these symbols are still seen in some healthcare settings, and oftentimes the apothecary measures may appear alongside the metric symbols on labels. For these reasons, it's important for us to be familiar with the apothecary system. So this unit brings together the fundamental skills of the previous units and applies these basics to healthcare situations. Although you will learn new information in this unit, the processes for arriving at the correct answers depends on our ability to compute using fractions, decimals, ratios, and proportions, and sometimes percents. So we've already been doing that. This will cover apothecary measurements and two methods of converting among measurement systems. So these fundamentals are going to help prepare you for math applications in the healthcare setting and for our role as surgical technologists. Well, the apothecary system is an old measurement, like we said, that originated in England. So this system, which uses grains for weight and minims for volume, is used by physicians and pharmacists to calculate drug amounts. It relies on several number systems to denote measurements: lowercase Roman numerals, Arabic numerals, and fractions. Although this system is being replaced by metric units, as discussed, to make the measuring system more uniform and avoid medication errors. We're discussing this system because you may encounter the apothecary units of measure, as some physicians still use this system as a matter of habit, right? The old school guys. So until the apothecary system is completely converted over to metric units, you may see labels, prescriptions, and doctor's orders using some of these units that we're going to discuss. So let's talk about some basic rules of when working with the apothecary system. So the first rule is that fractions of 1/2 may be written as SS. All right, that is the abbreviation for 1/2. So an example that you might see is nurse will give grains, ISS, of medication to the patient. Rule number 2, lowercase Roman numerals used for amounts that are less than or equal to 10 and 20 and 30. So here's an example. Doctor prescribed grains X, which would be 10 of the medication. Rule number 3, a symbol placed before a quantity, for example, 7.5 grains, equals grains V-I-S-S. V-I-I-S-S, right? So the V is 5, the I is 1, the I is 1, and SS means half, right? So an example would be pharmacist prepared grains IVSS of medication, which would be 4.5, right? The I coming before the V means 4, and then SS means half. Grains can also be abbreviated as GR. So it's important to remember that the metric and household measurements, the symbol follows the quantity. For example, 25 milligrams, 3 cups, 16 1/3 pounds. But in the apothecary measurement, the symbol is placed before the quantity. It's backwards. So there's 2 common symbols that you need to memorize in the apothecary system. And the symbol for fluid, ounces, and the symbol for grains are those 2. So you can see them here. Fluid ounce is like a Z with a 3 hanging on the bottom, and grains is capital G with an R. So approximate equivalence. Once you're familiar with these terms, symbols, and their equivalents, you're going to be ready to use the units in your conversions. This is a new concept for us to learn, right? When we think of science and measurement as exact, but apothecary is a measurement system of approximate equivalence. Approximate equivalents come into play when you are converting among measurement systems. Metric to metric or household to household measurement conversions usually can be done in exact measurements. In general, metric or household to apothecary measurement conversions are done through approximate measures. The equivalents are called approximate because they are rounded to the nearest whole number. In exact measures, 1 gram is equivalent to grains 15.432. However, the simple conversion in approximate equivalence used in healthcare is 1 gram equals grains 15. So to accomplish these conversions, you must memorize some of the approximate equivalents. To accomplish these conversions, like I said, there are some approximate equivalents that would be helpful if we memorize them. However, we do have a chart in the book that we can use for the purpose of this class, but when we get into the field, we might not have that chart readily available, especially if we're scrubbed in the operating room. So it would do us good to memorize these so that we could recall them easily and quickly. So notice that the conversions in the table are set up so that the unit elements are all on the left and that these will be placed on top of the known part of the ratio and proportion equation. So this simplifies the learning process, also expedites learning and helps us recall these conversions, and it's going to help us set up our problems. All right, so let's talk a little bit about how we do these conversions. So these conversions are accomplished by setting up the known and the unknown qualities in proportion format. We've already been using this, right? So let's use the following example as our guide. So here's the problem. How many milliliters are in 2.5 ounces? So to solve with the proportion format, we're going to set up the known conversion on the left. Set up what we know on the left and set up the part that with the unknown on the right. So when we set this up, we get 1 ounce over 30 mLs equals 2.5 ounces over X milliliters. All right, So now when we cross multiply 30 and 2.5, we get 75. And then we divide by the number that's left, and that is 1. And 1 goes into 75 times. So our answer is 75 milliliters. Don't forget your units. All right, so let's work through another example. Here, they want us to convert 48 milligrams to grains. So set up the proportion with the known information on the left and the unknown information on the right. So grain I, 1 grain, right, that's what that's saying, over 60 or 65 milligrams equals how many grains, that's our X, over 48 milligrams. So when we cross multiply, we get 48, right, because that I is a 1. It represents a 1, right, in Roman numeral. So 48 times 1 is 48, and then we divide by the number that's left, which is 60, and that, if we keep it in our fraction form, gives us 4 over 5, and that we write as grains 4/5. All right, so the dimensional analysis method is an alternative to the ratio, proportion, and dosage formula methods. There are no formulas to memorize. It's a problem-solving method that uses the fact that any number or expression can be multiplied by 1 without changing its value. Remember that in dimensional analysis, you can cancel like units if they appear in both the numerator and the denominator in any place in the equation. So let's work through an example. We'll use the one that we just did of how many milliliters are in 2.5 ounces. So we're going to place the unit of measure on one side of the equation. Question mark milliliters equals, right? That's the first step that we have there. Use the appropriate conversion factor. Use the conversion factor that is most appropriate to the problem. And then we're going to place the factor of the unit of measure for the answer on top and the unit that you are converting to on the bottom as the denominator. So then we're going to get question mark milliliters equals 30 milliliters over 1 ounce. All right, so remember we can cancel like units if we have 1 in the numerator and 1 in the denominator. So the first factor on the right side of the equation will have the same unit of measure as the unknown that's being solved for. So we're going to multiply the first factor by the given information from the problem. So we're going to add to the problem times 2.5 ounces over 1. We're going to cancel the like units, right? We can cancel ounces because it appears in the numerator and the denominator. Now both terms are over 1, so we can ignore the ones in the denominators. That leaves us with 30 milliliters times 2.5. So now we can solve by multiplying straight across, and that gives us 75 milliliters. Because milliliters is the only unit left. So sometimes when I do this, I will circle the unit that is left, and that's helpful for me. So in 2004, the Joint Commission created an official do not use list, and I believe this is posted in our class. And this list contains medical abbreviations that should not be used to reduce the risk and prevent errors in patient care. So problematic abbreviations can be misread. This is why we moved from cc's to mLs. So another example is micrograms used to be written as UG, which could be misread. Excuse me. So the preferred form is now mcg. So what if we have to complete multiple conversions? So it's best to work with the same unit of measure before changing to another unit of measure. For example, do all the metric conversions, then move to the grain conversions, or make the grain to metric conversion into milligrams, and then convert from milligrams to grams or micrograms. By doing this, we will have only one math setup per problem. Use the standard conversion equivalents to make the conversions. So let's look at our example. 0.0001 grams equals how many grains? So you may need to convert twice to get to a known conversion. First, convert from grams to milligrams. And remember our Kiss Hairy Dogs but drink chocolate milk mom? So that's our acronym for knowing how to move from grams to milligrams. So when we do that, we look at that acronym, we find that the decimal point needs to move 3 places to the right to get from grams to milligrams, right? So when we do that, we get 0.1 milligrams. Then we're going to set up with known equivalents for the conversion on the left, and we're going to put in our unknown stuffs on the right. So then we get grains 1 over 60 milligrams equals grains x, right, our unknown, over 0.1 milligrams. So convert the 0.1 to a fraction to ensure that you have the proper format in the final answer. Remember that grains is in whole numbers and fractions and not decimals. So we need to remember how to convert 0.1 milligrams to a fraction. And the way that we do that is we look at the decimal point and count how many numbers are to the right of it. In this case, there is 1. So we're going to set that 1 over a 1 and 1 0. So 0.1 milligrams becomes 1 over 10 milligrams, or 1/10 milligrams. Now, let's pause the video and work through this problem, and then we'll work through it on the next slide. Okay, so how did you do? Working our problem, we carry over the setup from the previous slide, and we're going to cross multiply I, which is 1, times 1/10 to get 1/10, right? 1 times anything is itself, right? So it's no different with a fraction. So when we cross multiply, we get 1/10, all right? Then we're going to divide 1/10 by the remaining number, which is 60. Remember, 1/10 divided by 60 is like 1/10 divided by 60 over 1. Now, remember, when we are dividing fractions, we reciprocal the fraction to the right of the division sign and change the sign to multiplication. So that gives us 1/10 times 1/60th, and that equals 1/600th when we multiply straight across 1 times 1 and 10 times 60. So our answer is grains 1/600th. So sometimes you will convert liquid equivalents in the same manner using ratio and proportion or dimensional analysis. So you'll need a wider range of conversions to convert liquid equivalents. So rely on the conversion charts, but work towards memorizing these equivalents so that you can efficiently apply them. We see the approximate equivalence chart that we took a look at before, and we can use that as a reference as we work through these problems. So the metric system is used to measure liquids, weights, and medicine. We know that, right? So rounding is used to ensure proper dosing. So to assist in this process, let's look at some guidelines that we should follow. So the first one is any decimal number that stands alone without the whole number must have a 0 placed in the whole number place. We've been talking about this since the beginning. 0.5 needs a 0 in front of the decimal point, right? So 0.5 or 0.25 or 0.125. We never just want to put a decimal and the numbers to the right. We always want to put a 0 before the decimal, all right? The second thing is round decimals to the correct place value. So this is somewhat dependent on your profession. However, some general guidelines do exist. For example, kilograms and degrees in Celsius and Fahrenheit are placed to the tenths, which you already talked about. But what I see typically in the field that we work in is rounding to the hundredths place. So we can go ahead and apply that to the rest of the work that we do when we're working with these different conversions. So the third thing is multiple step problems require that you convert between number systems, especially between fractions and decimals. So if the if the drug measurement is in metrics, like milligrams, grams, or micrograms, the solution to the problem needs to be in decimals. Remember, metrics is decimals. Standard or household systems and apothecary systems are in fractions. So if we have something like a 1/4 milligram, we're going to write that as 0.25 milligrams. The fourth thing is we don't want to over round. We want to save our rounding for the very end. In medications, a small amount of medication can be critical in dosing. Like I've mentioned before, it is critical in adults as well as pediatrics, but with children, a small variance in a dosage could end a life. So we want to make sure that we begin to round, we get into the habit of rounding at the end of the problem and not as much at the beginning of the problem. So a good rule of thumb is going to be for us to round when we get to our final answer. And lastly, the trailing 0. The trailing 0 is used to show the exact level of each value, such as a lab result, the size of a lesion, or a catheter size. So use a trailing 0 only when necessary, right? We're usually going to take those trailing zeros off at the end. The Joint Commission notes that the trailing 0 should not be used. This is for safety and to avoid us misreading amounts. So that concludes our review of conversions of the apothecary system. And now we're going to move into talking about dosage calculations. So at the end of this chapter, we should be able to calculate dosages with the dosage formulas that you've been given and or dimensional analysis. We should also be able to use drug labels to gather dosage information to calculate the supply on hand. So we've been looking at labels, so we're training our eye to see the pertinent information on the label. We'll also be able to convert among systems to calculate doses, and lastly, convert a drug order to the format of the supply on hand. So let's get into it. So this unit pulls together all the math skills that you have reviewed, you and I have reviewed, and practiced previously in this course. So our task in this unit will be to determine the individual dose of medication that a client will receive, or a patient for that matter. So this is a common task for us in the medical field, and so let's get into this unit. So in order to calculate an individual dose, we need to know three important pieces of information: the desired dose, which is represented by a D, the dosage strength, represented by an H, and the unit of measure, represented by a Q. So let's take a closer look at what D, H, and Q mean. So remember that D is the dosage ordered or the desired dose. The meaning of this is that it's the amount of medication that the physician has ordered for the patient. And an example could be give 500 milligrams. The dosage strength or supply on hand, or what we have, is going to be represented by the symbol H, and that is the amount of drug in a specific unit of measure, and you may see it written as 25 milligrams per 5 grains, or grains 5. And the unit of measure, or quantity of unit, is Q. And this is the unit of measure for the specific dosage strength or supply on hand. So 250 milligrams per 2 mLs, or 30 milligrams per capsule, 25 milligrams per tablet, so on and so forth. Okay, so let's talk through a medication order. Here, the physician ordered sertraline HCl 50 milligrams once a day. All right, so is this the D, the H, or the Q? If you chose D, you would be absolutely right? D is the dosage that the physician ordered for the patient. Now, let's look at the medication label. The medication label says that it is sertraline HCl 25 milligrams per tablet. So what does 25 milligrams represent? It represents the H, right? It's what we have. And the quantity, the Q, is per 1 tablet. Okay? So again, the dosage ordered and the supply need to have the same units. D and H need to have the same units. So if they don't, we may need to do some conversions before we can figure out the medication that needs to be given, right? And then the quantity and the unknown, so the Q and the medication given, those need to be in the same units. All right, so again, if they're not, then we're going to have to do a little more work before we can actually plug the stuff into our problem. So if we can memorize this formula, that would be really helpful when we're performing these dosage calculations. And also we need to make sure that we are making formula substitutions properly. Remember, D over H times Q equals X, or the unknown dosage? How much medication do we actually give? So again, the desired or dosage ordered over supply on hand times quantity is going to equal our unknown dosage. All right, so let's work through an example. First, we're just going to practice setting up a problem, and then we will work through a problem. So here it gives us the known information, D equals 50 milligrams, H equals 25 milligrams, and Q equals 1 tablet. So again, if we know our formula, D over H times Q equals X, we can plug in. Let's start. We have our 50 milligrams, and that is our D, right? All right, and then we're going to set that over H, which is 25 milligrams. Okay, 25 milligrams. Now let's look and see if the units of the D and H are the same. And yes, they are. They're both milligrams, so we're good there. And then we're going to times this by the quantity. And it tells us the quantity is 1 tablet. All right. For sake of space, I'm not going to write tablet, but I think it's a good idea that we do when we're working these out. And then that is going to equal our X. Okay. So this is the way that we would set up this problem. 50 milligrams over 25 milligrams times 1 equals X. All right, let's look at another example. We're actually going to work through this one this time. So the physician, it tells us, ordered 250 milligrams. This represents, right? And this represents D, right? The dosage that the physician ordered. And when we look at the label, we see that the label says there's 125 milligrams per tablet. So the 125 milligrams represents what? That's right. It represents H, what we have on hand, okay? And then the tablet represents quantity, right? Our Q. All right, so now we know what parts we are working with here. All right, so let's go ahead and set up our problem. All right, we have D over H times Q equals X as our formula. And we're going to go ahead and set this up as 250 milligrams over H, which is 125 milligrams. Now let's just pause right here and make sure our units are the same. And they are, they're both milligrams, right? So times Q, which is 1, is going to equal our unknown. All right, so take a couple minutes, pause the video, work this out, and then come back to see if you got the right answer. So now we're going to solve our problem. And to do this, first we need to deal with the 250 milligrams over 125 milligrams. And we're going to simply divide 125 up into 250. And when we do that, we get 2. All right, and then we've taken care of that. Now let's look at what the rest of our problem is. 2 times 1 is going to equal our unknown, right? So when we do 2 times 1, we get 2. And so 2 is going to equal our X. All right, and so this tells us that we need to give, in order to give the patient the correct dosage that the doctor ordered, we need to give the patient 2 tablets of medication. Okay, so let's look at another example. A detailed section on using dimensional analysis is in Appendix D for our reference, and other applications of dimensional analysis are also shown in Units 10 and Units 12. So those are some good resources for you. Okay, so again, let's tackle the order. The physician's order is Zithromax 500 milligrams. Now, what part of our formula is that? Right, that's D, right? Okay. The supply on hand is Zithromax 250 milligrams per tablet. So 250 is going to equal our H, what we have on hand, and the tablet is going to equal our quantity. That's our Q. All right, so let's go to the next slide and we will set up our problem. All right, so we have our formula of D over H times Q equals X. So our D is going to be our 500 milligrams, right? 500, that should be a 0. 500 milligrams over our H. Our H, it tells us, and we determined on the prior slide, that it's 250 milligrams, and then that is times 1 tablet, again for sake of space, I'm not going to write tablet, but I think we should, equals X. All right, so go ahead and pause the video and work this out, and then come back and we'll go through it together. Okay, so the first step here is to divide, well, first let's just take a step back and make sure our units are the same, and they are. So we're going to divide 250 into 500, and that is going to give us what? That gives us 2, right? Alrighty. So then 2, let's look at the rest of our problem. 2 times 1 equals our X. And when we do our multiplication, we get 2 equals X. So again, what this is telling us is that we need to give the patient 2 tablets of medication to arrive at the 500 milligrams that the doctor ordered. So remember how we talked about using dimensional analysis to solve problems or do conversions, and so let's just walk through a example using dimensional analysis. So here the doctor orders 60 milligrams of a liquid cough syrup, and the liquid cough syrup has a label that reads 100 milligrams in 5 mLs. So let's look at, on the next slide, how we can set that up. So let's set up one of these problems using dimensional analysis. Now, the way that we would do that is first we are going to place the unknown on one side of the equation. And what we don't know is mLs. That's what we're looking for. How many mLs of medication are we going to give this patient, right? Okay, so that is going to equal our unit of measure over the dosage strength. So it tells us there's 5 mLs of medication. If we give that to a patient, they're going to get 100 milligrams of the medication. Okay, so we're going to set this up as the unit of measure, which is 5 mLs, over the dosage strength 100 milligrams of medication in 5 mLs. All right, and then we're going to multiply that by the dosage placed over the number 1. All right, the dosage is the D, right? This is the dosage right here. So that is 60 milligrams. And we can place that over 1. All right, so here we're going to cancel our like units. Remember, if a unit appears in the numerator and the denominator, we can cancel that out. So we're going to cancel out the milligrams, right? And that is going to leave us with the milliliters. We're going to multiply straight across. And when we multiply straight across, that gives us 300 over 100, all right? And 300 over 100 is the same as 3. So our answer is going to be 3 mLs. We need to give 3 mLs of this cough syrup to the patient in order to give them a 60 milligram dosage. All right, so now that this formula is familiar to you, the next step is to apply the metric and apothecary conversions you used in Unit 10. So convert the unit of measure of the ordered and have to the same unit of measure. So usually one thing that makes it easier is to convert the order unit to the have unit and not the other way around. So this also helps in being able to compute the answer. So once the units are identifiable, then it's easy for us to make the conversions. All right, so let's work through a couple problems before we go regarding converting among systems. So the first one says that the doctor ordered 1 gram of medication to be given. And what we have is 50 milligrams in 2 milliliters. All right, so let's figure out first our D, H, and Q, right? This is pretty much how I start all of these problems. Let's figure out our D, H, and Q. All right, so what is the D? Yes, the D is what was ordered, and that is 1 gram, okay? The H is what we have, right? And it says we have 50 milligrams. 50 mgs, and then it's telling us the quantity is dose milliliters, okay? So now we have our parts of our equation, but let's look at the D and the H. Are the units the same? Nope. Nope. They're not the same. So the first thing that we have to do is convert the ordered to the have. That's going to be easiest. So what that means is we need to convert grams to milligrams. Remember how we do that? We look at our acronymic sentence and we find our base, grams, and we need to move the decimal point 3 times to the right, or we need to multiply by 1,000. So when we do that, right, 1, 2, 3 jumps, that is going to give us 1 gram is equal to 1,000 milligrams. All right, so now we're good to go. All we have to do is plug in our information into our equation and we'll be able to solve, right? So remember our equation is D over H times Q equals X. So the D is 1,000 the H is 50 milligrams. And that is going to be times our quantity, which is 2 mLs. All right, and that is going to equal our unknown. So when we solve this, the first thing that we can do is divide 50 into 1,000. And when we do that, we get 20. All right, so then we got to look at the rest of our equation, which is the times 2 mLs. And that is going to, when we perform this, right, that is going to give us an answer of 40 mLs. Actually, these units wouldn't be here because they cancel out, right? Numerator, denominator, right? So we're left with 40 mLs as our answer. So let's look at a second problem. So here's our second problem. The physician ordered 0.5 grams of a certain medication, and what we have on hand is 200 milligrams per tablet. All right, so again, the first thing that we want to do is dosage, have, and quantity. All right, so the dosage, the have, and the quantity. Okay, so what is our dosage? Our dosage is 0.5 grams, right? 0.5 grams. There's a point in there. Our have is 200 milligrams. And let's go up and put our units on here so don't forget that. And then our quantity is 1 tablet. 1 tablet. Okay, so let's look at our dosage and our have. Are they the same units? No, they're not. So the easiest way is to convert what was ordered to what we have, right? And to do this, it's the same operation we performed in the last example. We're going to multiply by 1,000 or move our decimal point 3 times to the right. And when we do that, we get, what do we get? 500 milligrams. 500 milligrams. All right, so now we can go ahead and set this up and solve. So pause the video and work through this problem, and then come back and we'll set it up and work through it together. Okay, so let's go ahead and set this up, right? We have our D over H times Q equals X. So our D is our 500 milligrams. 500 milligrams over our have, which is our 200 milligrams. And then we're going to times that by the quantity, which is 1 tab. I'm not going to write tab, but we should, equals X, right? How much medication we need to give. So first things first, divide our 200 up into our 50, all right, and we get 2.5. And we're going to remember the rest of our equation, which is times the quantity, which is 1. And when we multiply, that is going to give us 2.5 tabs. But really, when we're writing tabs, we should probably put it into its fraction form. And so that is going to give us 2.5 tabs as our answer, and that is what we would give our patient. Okay, so that includes our lecture on Unit 11 and 12. I hope you found it helpful, and I look forward to working with you in class and answering whatever questions you might have. Thank you for taking the time to listen to this lecture.